There are also some reductions that we can do taking carboxylic acid derivatives or +3 compounds like amides and nitriles all the way down to +1. But these are very stable compounds. Remember that these are at the bottom of the reactivity ladder. So they're pretty much inert or will not react with the weak reducing agents. And so if you're going to reduce them, you have to use a strong reducing agent, aka lithium aluminum hydride. So let's recall a couple mechanisms for how we make amides. First, from an acyl chloride, where this nitrogen is 5 atoms away from the carbonyl, and primary amine can attack to give you a zwitterionic intermediate. And chloride is always a better leaving group than any nitrogen atom. So that's going to dissociate to reform the carbonyl and expel chloride. So remember that the addition step for these addition eliminations is generally slow, and elimination is usually fast, especially if you have a good leaving group like chloride. And then from there, the reason that we have a tertiary amine, triethylamine, is to mop up the acidic byproduct or to prevent the formation of HCl and obtain the neutral secondary amide. So we've seen that we can make an amide from an acyl chloride because the acyl chloride is a +3 or carboxylic acid derivative oxidation state. It has a viable leaving group. We just need a base so that we can mop up the acid that's made. So let's look at a couple other reactions of these. Going here from the primary alcohol to the amide, or from +1 oxidation state to a +3. So obviously we must oxidize, and going from +1 to +3 means you have to use a strong oxidizing agent, like chromic acid. And that'll take you to the carboxylic acid, where this will remove both hydrogens from the primary alcohol. And now we're in the correct oxidation state to make a carboxylic acid derivative like an amide. The problem is you can't just add this diethylamine because that amine is basic and it would just deprotonate the acidic alpha proton there on the carboxylic acid. So instead, what you have to do is turn this into some other carboxylic acid derivative, and the chloride is always a great option because the chloride has an even better leaving group that's not acidic and can be made irreversibly with thionyl chloride. From there, you just add your diethylamine to do the same mechanism that we did above, where nitrogen attacks and displaces chloride. And you also would need triethylamine or pyridine as an exterior base. Of course, instead, if you wanted, you could just use 2 equivalents of the amine to give the product. So there, we want to oxidize up to +3 and then make the amide once we're in that correct oxidation state. The problem is you can't make the amide from the carboxylic acid directly because you'll just get an acid-base reaction. So in this compound, now we have 2 carboxylic acid derivatives, an ester and a carboxylic acid itself. And I'm adding 2 equivalents of the amine. The first equivalent is going to do acid-base chemistry. because this proton here is acidic. So the nitrogen will deprotonate and leave a negative charge on the oxygen. And that acid base is fast, so it happens first. But thankfully, we have a second equivalent of the amine, which will not attack the carboxylate, right? That is not electrophilic, or it has a negative charge. But the amine will attack the electrophilic carbonyl that remains, the ester. So when it attacks the ester, it takes you to this zwitterionic intermediate, where we have a positive charge on nitrogen and a negative on the oxygen. From there, you could do a proton transfer or deprotonate the nitrogen so that the oxygen is the better leaving group. Okay, so now the last step to make the amide is just to collapse and kick out the oxygen leaving group, and that breaks open this bridge bicycle. So now we have a 6-membered ring where there's an O minus, okay, and that is 1,3 to the carboxylate. And there's also a newly formed CN bond. And you get this tertiary amide. And that O minus can go on to protonate with the acid that we just made in the previous step. Protonate here, giving the neutral alcohol product. Okay, so that goes from an ester to an amide, which is a downhill step on the reactivity ladder, and therefore favorable. Okay, one more example with this. So if you take an acid chloride, which of course is the most reactive carbonyl or carboxylic acid derivative, and you treat it with sodium borohydride, that will reduce after acidic workup all the way to the primary alcohol. If you're trying to make that alcohol into an electrophile, one excellent way to do that in synthesis is to use this reagent PBr3, where now the alcohol is substituted for via SN2 by a bromide. And finally, after that reaction finishes, sodium cyanide will do another SN2 to furnish this final nitrile. So notice that if you were making this nitrile in synthesis, that you've gone down from +3 to +1. So that's accomplished by a hydride reagent, lithium aluminum hydride or sodium borohydride. But the alcohol is not electrophilic. So if you ever want to make a new carbon-carbon bond with sodium cyanide, we make it into an electrophile first by turning it into a good leaving group, which is the bromide compound. Okay, So I think I'll finish here with this next mechanism explaining how the +3 or the amide reduces down to the +1 oxidation state, the amine. And there's a couple more pages after this that have some synthesis problems that I will complete the key for, and you guys can use those as a practice to see if you understood the topics from today. So if you take amide A, it fails to give this partially reduced product, B. This is not observed, but instead, the major product is this tertiary amine. And like I said earlier, the amide is super stable. You have to use the strong reducing agent to get it to go. So this strong base, good nucleophile aluminum hydride has no problem going in and just attacking the carbonyl directly. That will lead to a tetrahedral intermediate where there's a new CH bond and it's been reduced one step, but there's no obvious leaving group to eliminate because the nitrogen is a bad leaving group or a strong base. But don't forget that oxygen loves aluminum, which we saw in Friedel-Crafts chemistry. And that oxygen will bind to aluminum to give this intermediate, where you now have a negative charge on aluminum again. And lithium is sitting here as a counterion the whole time. So now what happens is the oxygen is going to act as the leaving group because it's a weaker base than nitrogen, and that's why the oxygen is not in the product. Or the nitrogen will form a lone or a pi bond with its lone pair and push out that oxygen leaving group. So this is why the amides reduce to amines where the oxygen is entirely gone. This puts O- into solution next to aluminum. And what we now have is an iminium ion. And we said these were super electrophiles, or they're so electrophilic at carbon that even that weak reducing agent would attack them. So for sure, the aluminum hydride will attack and fully reduce it down to the final amide or the final amine from the amide. So we've got these two new H's here, or a tertiary amine product. Now, once again, all of the +3s or carboxylic acid derivatives do reduce to +1, but it's the nitrogen-containing ones, the nitrile and the amide, that do not give alcohol products. They give amine products instead because the oxygen is a better leaving group than nitrogen. Now, you always wash out the aluminum with water and acid. And when you add water and acid, remember that your amine is basic, so it will fully protonate. So if you want a neutral amine that you can extract in a nonpolar organic solvent, then you have to do a third step here where you take off the proton again with a strong base. So you'll see hydride, then acid, then base is the three-step procedure for reduction of an amide. And they give amine products where the oxygen is entirely gone. So you want to use a lot of these carbonyl reactions for making the new CN bonds, and then use the reductions I taught you today for reducing from the carbonyl either +2 or +3 oxidation state all the way down to +1.